When PyTorch computes W.grad, it is answering a very specific question for each of the millions of weights in your model. If I change only this one weight by a tiny amount, while holding every other weight perfectly fixed, how does the loss change? That answer is a partial derivative. Not the total derivative, the partial derivative. And every weight gets its own. A model with 175 billion parameters computes 175 billion of these partial derivatives per backward pass. Today, formal definition, computation rules, gradient vector, the Hessian matrix, and how partial derivatives appear in 4 different layers: embedding, softmax, BatchNorm, and LayerNorm. The formal definition of the partial derivative of f with respect to x_i at point A is the limit as h approaches 0 of f with x_i replaced by x_i plus h minus f at A, all divided by h. Every other variable is held at its value in A. This is exactly the ordinary one-variable limit definition, applied to a function of many variables, with all others frozen. To compute a partial in practice, treat all other variables as constants. Differentiate normally using the power, product, or chain rule on x_i alone. Repeat for every variable you need. 3 examples. F equals x squared y plus 3y squared. Partial with respect to x, treat y as constant, apply power rule to x squared y, result is 2xy. Partial with respect to y, treat x as constant, x squared becomes a constant coefficient, apply power rule to 3y squared, result is x squared plus 6y. For the dot product W transpose x, partial of the sum over I of W_i times x_i with respect to W_j is x_j, only the jth term survives. So the gradient of the dot product W, R, T, W is just x. By symmetry the gradient W, R, T, x is W. 4 partial derivatives that appear in every training loop. 1. Linear layer weight gradient. Z equals W times x plus b. Partial of z with respect to W_ij is x_j, the jth input element. So the full weight gradient is the outer product of the upstream delta with the input activation. Bias gradient is the upstream delta directly, because partial of z with respect to b is identically 1. 2. Attention gradient. The attention score is q times k transpose divided by root d. Partial of the score with respect to q_ij is k_ij divided by root d, treating all other q and k elements as constant. 3. BatchNorm scale gradient. Output y equals gamma times x hat plus beta. Partial of y with respect to gamma is x hat, the normalized input. So the gamma gradient sums the product of upstream gradient and normalized input over the batch. 4. Embedding layer. The embedding matrix E has 1 row per vocabulary item. The partial of L with respect to E_ij is non-zero only for the row corresponding to the current token. All other rows have 0 partial because they don't appear in the forward computation. This is why embedding gradients are sparse. Second partial derivatives measure curvature. The Hessian matrix H of F stores all second partials. H_ij equals partial squared F over partial x_i partial x_j. The diagonal entries are the curvatures in each coordinate direction. The off-diagonal entries measure coupling, how changing x_i affects the gradient direction x_j. By Clairaut's theorem, if f is twice continuously differentiable, the order of differentiation doesn't matter. H_ij equals H_g. The Hessian is symmetric. the eigenvalues of H classified critical points. If all eigenvalues are positive, we are at a local minimum. The loss surface is bowl-shaped in every direction. If signs are mixed, we are at a saddle point. Some directions curve up, some curve down. If eigenvalues are near zero, we are in a flat region. For neural networks, saddle points are far more common than local minima. The condition number of H, largest eigenvalue divided by smallest, determines how elongated the loss bowl is. High condition number means gradient descent zigzags slowly. Adam's second moment v_t approximates the diagonal of H, providing per parameter curvature correction without inverting H or AI-specific partial derivative computations. 1. Embedding gradient. Only the active token row receives a non-zero gradient. All other embedding rows have zero partial. Sparse gradient accumulation. PyTorch uses sparse tensors for this. 2. Softmax Jacobian. The partial of softmax output p_i with respect to log at z_j is p_i times the Kronecker delta of I and j minus p_i times p_j. In matrix form, the Jacobian of softmax is diagonal p minus the outer product p times p transpose. When combined with cross-entropy loss, this collapses to the clean gradient p_i minus y_i. 3. L2 regularization. The partial of 1/2 times lambda times the squared Frobenius norm of W, with respect to W_ij, is lambda times W_ij. This adds lambda times W to every gradient step, weight decay. 4. LayerNorm backward. Because LayerNorm normalizes across features, changing one input x_i changes the mean and standard deviation for the whole layer, which changes every output. The partial is coupled. Partial differential L, partial differential x_i involves three terms: direct path, path through mean, path through standard deviation. This coupling makes LayerNorm backward more expensive than BatchNorm for wide layers. 5 things cold. 1. Partial differential f, partial differential x_i, vary x_i, freeze everything else, apply the limit. 2. Gradient vector stacks all partials in the same shape as the parameter, subtracting it gives gradient descent. 3. Hessian h_ij stores all second partials, symmetric if C2. 4. Eigenvalues of H classified critical points. Positive definite is minimum, mixed is saddle, near zero is flat. 5. Adam's second moment approximates the diagonal of H for curvature correction. Exercise. For f equals x squared y plus sin of xy, compute all 4 second partials analytically. Verify each one numerically with central differences using h equals 1e4. You now understand partial derivatives at the level you need to debug any gradient in any layer. Every W.grad is a partial, one variable at a time, all others frozen. The gradient vector stacks them all. The Hessian carries their second-order extensions. And Adam's second moment is, essentially, an online approximation of the diagonal of the Hessian, giving curvature-aware steps without the O(n³) cost of inverting the full matrix. Video 22 is Gradient Descent Algorithms, SGD, Momentum, RMS Prop, Adam W. Each one is a different strategy for using these partial derivatives to navigate the loss landscape. Subscribe so video 22 is ready. Post your answer to the Hessian eigenvalue question in the comments. See you in video 22.